Hey friends, welcome back. Have you ever wondered how a small, lightweight adapter can take dangerous 230-volt AC mains power and safely convert it into a steady 12-volt DC output without getting hot or heavy like old-style transformers? That's exactly what we're breaking down today, how an SMPS, or switch-mode power supply, actually works.
Here is the complete schematic we'll be using as our example. A 12-volt, 5-amp SMPS circuit built around the top 227YN IC. Keep this in mind as we go, because now we're going to bring this entire circuit to life in 3D and walk through exactly how mains AC gets transformed into clean, regulated DC, stage by stage.
Inside every SMPS, the power actually goes through 3 separate conversions: AC to DC, then DC back to AC at a very high frequency, and finally, AC to DC one more time. It sounds strange that DC gets converted back into AC in the middle, but there's a good reason for it. Transformers can only work with changing current, not steady DC. So the SMPS deliberately creates a high-frequency AC signal just so it can pass through a small transformer. This one trick is exactly why SMPS units can use a tiny transformer instead of the big, heavy ones found in old-style power supplies. And you'll see this AC, DC, AC, DC journey happening right in front of you as we go through the circuit.
The very first job of any SMPS is to take the incoming AC and convert it into DC. Mains power enters through the input connector, passes through a fuse for overcurrent protection, and then through an NTC thermistor, which limits the sudden inrush current that happens the split second you power on the device. Before rectification, the AC also passes through an EMI filter, made up of a dual-wind choke coil and small safety filter capacitors. This step is incredibly important because it blocks electromagnetic noise from entering the circuit and also prevents the high-frequency switching noise generated inside the SMPS from leaking back onto your home's mains line.
Next comes the bridge rectifier, made of 4 diodes, which converts the AC sine wave into a pulsating DC waveform. This pulsating DC is then smoothed out by a large, high-voltage electrolytic filter capacitor, giving us a steady, high-voltage DC bus of around 325 volts. This marks our first conversion complete, AC to DC. Now here is where the second conversion begins, DC back to AC. Instead of using a heavy 50 Hz transformer like traditional power supplies, an SMPS uses a switching IC that turns this 325-volt DC on and off at a very high frequency, typically over 100,000 times per second. This critical job is done by the TOP227YN, which conveniently packs a built-in high-voltage MOSFET, an oscillator, and protection circuits, all inside a single chip.
When this internal switch turns on, current flows through the primary winding of a small ferrite-core transformer, and energy gets stored as a magnetic field inside its core. When the switch turns off, that stored energy is released into the secondary winding. This rapid on-off switching action, called the Flyback principle, is what allows the transformer to be so much smaller and lighter than a normal mains transformer, since a higher switching frequency means far less magnetic material is needed to transfer the same amount of power.
A Snubber network made of a resistor, capacitor, and diode sits directly across the primary winding to absorb high-voltage spikes created during switching. This protects the internal MOSFET from being destroyed by voltage spikes when the magnetic field collapses. On the secondary side, our third and final conversion happens, AC back to DC. The high-frequency energy released from the transformer is rectified using a fast Schottky diode and then smoothed by an inductor and low ESR output capacitors. This final filtering stage removes the high-frequency ripple, leaving us with a clean, stable DC voltage at the output, in our case, 12 volts at up to 5 amps.
But converting the voltage down is only half the job. An SMPS also needs to keep that output voltage constant, even when the load changes or the input voltage fluctuates. This is done through a feedback loop, where a voltage divider samples the output voltage and feeds it to a precision reference IC, the TL431,
which compares it against a fixed internal reference. If the output voltage rises even slightly above 12 volts, the TL431 responds by driving more current through an optocoupler's internal LED. Since the primary side and secondary side of an SMPS must be completely isolated for safety, this optocoupler is what carries the feedback signal across that isolation barrier, using light instead of a direct wire. On the primary side, the optocoupler's phototransistor picks up this light signal and feeds it back into the switching IC's control pin. Based on this feedback, the top 227YN automatically adjusts its duty cycle, meaning it changes how long the internal switch stays on during each cycle, which corrects the output thousands of times every second to maintain tight and stable voltage regulation.
AC mains is converted to DC, chopped back into high-frequency AC by the switching IC, transferred through a compact transformer, converted back to DC one final time on the secondary side, and finally regulated through an isolated feedback loop. This is exactly why modern SMPS units are so much smaller, lighter, and more efficient than old-style linear power supplies, and why you'll find this same basic working principle inside mobile chargers, laptop adapters, LED drivers, and countless other devices around you. If this explanation helped you understand SMPS working clearly, do hit that like button, subscribe, and let me know in the comments if you'd like a deeper dive into any specific stage of this circuit. Thanks for watching, and I'll see you in the next video.